Okay, in this video, we will continue on with chapter 2, Benzene and Aromaticity. We will go into the second subtopic, which is on the nomenclature, and in other words, naming. Okay, so we're going to name the structure of benzene. Now, for naming aromatic compounds such as benzene, okay, most common names are used like toluene or aniline. It's acceptable, okay, it is an acceptable common name for the compound. Alright, so toluene is actually the common name for methyl benzene. So we have the benzene as the parent name, and the substituent here is a methyl group. Okay, so hence, following the IUPAC naming system, it is called methyl benzene. Whereas for aminobenzene, okay, this is amino, and the parent is benzene, so aminobenzene is the IUPAC name. Common name would be aniline. So later in your final exam, if let's say they do, when you read the question, sometimes they will ask for IUPAC naming. So you have to be very careful if they mention IUPAC. If they ask for IUPAC, that means you have to use methyl benzene. But if let's say they do not show IUPAC, they just say name the compound, okay, then you can use the common name like benzene. Oh, sorry, like toluene. Alright, the common name for benzene, methyl benzene, like such as toluene or aniline, so it's acceptable. So be very careful if whether or not they mention that they want the IUPAC name, because if they don't mention that they want the IUPAC naming, then you can give the common name. Right? So these are mostly known as monosubstituted benzene. Monosubstituted means mono means one. So later on we have the di substitute and tri substitute. So di will have 2, this one will have 3. So monosubstitute means we have one substituent attached to the benzene ring. Okay, so systematically names as hydrocarbon with benzene. So benzene parent, so the substituent will be the prefix here. Alright, so we have bromo for bromine, and we got nitro for NO2, and then propyl. Okay, this is an alkane. So when an alkane is a substituent group, is known as an alkyl. Okay, we have already covered this. Now, when benzene ring, okay, benzene ring can also be a substituent. Now, when it is a substituent, it is called a phenyl. So a phenyl. So this is how it will look like. It is directly attached to the benzene ring. This is a phenyl group. Okay, so in this case, like we have this phenylheptane. Okay, why is the benzene ring the substituent, whereas the heptane the parent name? Okay, heptane has more carbon as compared to the benzene ring, so that's why heptane in this case takes the parent name. But in some cases like this case, whereby you have only 2 carbons, but because of the presence of the substituent OH is attached to this carbon and not to this carbon, okay, so meaning to say this part, this one would be the parent. That's why we use ethanol. Okay, and the P and the benzene ring here becomes a phenyl. So phenyl ethanol. One phenyl, one ethanol. Okay, another thing here I want to note is that when we have benzene ring, and then you want to know what is the situation, where is it situated at carbon number 1. Normally, if it's monosubstituted means only 1, right? So if it's only 1, normally it will consider where the carbon is attached to is carbon number 1. So let's go back to this one here. You notice that we don't use 1 here. Actually, you can put 1. Alright, you can put 1, or if you don't put also, it's still correct because it's only a monosubstituted benzene. There's only 1, so automatically the carbon that attached the substituent is carbon 1 automatically. Doesn't matter how you draw it, whether if you draw it in the opposite direction like such, okay, it will still be bromobenzene because it's only 1 substituent present. So automatically this is carbon 1. Whether clockwise, anti-clockwise, it still be the first carbon. Okay, so now we have the benzyl group. So what is different with the benzyl group is this part. Alright, if you notice, this is attached, the carbon chain is attached to the benzene ring, but this one, the carbon chain is attached to another carbon. Alright, it is attached to another carbon attached to the benzene ring. So if it is not directly attached to the benzene ring, okay, this is a benzyl group. Okay, it must have this carbon here, then only you see the benzene ring. This is a benzyl group. Okay, so this is a substituent as well. Okay, so in this case, just now we have one phenyl, one ethanol. So it's the same. Ethanol will take the parent, right? Because there's two carbon, ethanol. But now, because it is not attached to the carbon that has the OH, but is attached to the second carbon here, so it becomes like this, if you notice. Alright, so because of that, we don't call it a phenyl anymore. Now it's called a benzyl. So you have to be very careful with these two particular groups. When you do naming of benzene, you have to look at the structure properly, whether it is attached directly to the benzene ring, or is there another carbon attached to the benzene, then only attached to another carbon chain. So it will make a lot of difference in your naming, especially when it is a substituent group. So here are some examples of monosubstituted, and we have the O-xylene here is di-substituted. This is tri. Okay, so mono, these are all monos because substituted only on one, okay, on one carbon on the benzene ring. So these are all acceptable names. Okay, these are all the common names. Common name. Except for benzene sulfonic acid. Benzene sulfonic acid, this is also acceptable as a IUPAC name. Okay, this one will come into the next slide, right? So di-substituted benzenes, we have the relative position on the benzene ring. We have the auto, meta, and para. I think I mentioned about this earlier in, I think, when we were covering chapter 4. Okay, auto, meta, para. Right, so auto, meta, para. So if Autometapara is only used for di-substituted benzene, means there are two substituent presents on the benzene ring. So in this case, if it's ortho, it should be next to each other. If it's meta, it will be one carbon apart, and if it's para, it will be two carbon apart, okay, on either side. So here, simplified, describe the patterns, auto, meta, para. Okay, so here we have a reaction. This is a form of reaction. Okay, so if we have the presence of CH3 already, okay, normally di-substitute benzene, we have already a substituent present. Then we add in another substituent to get a di-substitute benzene, like para-bromotoluene. Okay, so if we're adding the same substance, we're adding, sorry, not the same substance. So in this case, we have the presence of the methyl group already. Now we want to add in a halogen to this toluene. Okay, the reaction is here. Okay, so what happens is that it will give you another product, that is the bromotoluene. Now how do we know whether the product will come out here, come out here, come out here? Okay, so this one later on will go into in the later part. Okay, in the later part of this chapter, after we have introduced the reactions, okay, I will teach you how to determine the presence of the substituents that are directing in which order. Okay, in each, it will direct the positioning of the second substituent that is included. Okay, they're trying to introduce a second substituent. Okay, so here, if it is toluene, okay, toluene, we add bromine, we'll get a bromotoluene, so we will get a para-bromotoluene. Why? This is to do with the directing effects of the presence of the already present substituent methyl. Okay, so here there are some more examples whereby we have ortho dichlorobenzene, meta dichlorobenzene, para dichlorobenzene. So for the naming, if it is a disubstituted benzene, then you can use auto, meta, or para to describe the positioning. But if it is tri, then you can't use Autometapara, you must use the number. So if let's say you don't want to take the risk and you don't want to use Autometapara, you can also still use the number system. Okay, but be very careful to be able to identify which would be the first carbon or the second carbon or the third carbon or the fourth carbon. Alright, so in this case, like in this first diagram here, it is a dichlorobenzene. So dichloro, both are chlorine, so no issues there. 1 and 2, either way should still be 1 and 2. Now meta, okay, if you go anti-clockwise, you get 1, 2, 3. If you go clockwise, you end up with 5. So why we take this side? Because 3 is smaller than 5. I'm sure you still remember that. Alright, so the same goes for para. Okay, the same goes for para. Right, find the lower configuration, the lowest value, right? So naming benzene with more than 2 substituents. Okay, so now we have more than 2. Okay, choose numbers to get the lowest possible value. Okay, always list substituents alphabetically. Okay, common names such as toluene can also be used as root name. Alright, so these are the 3 rules that we've already been introduced previously since chapter 1. Okay, lowest value, alphabetical. Okay, right. Now rules to naming aromatic compounds is actually quite similar to the rules for naming other hydrocarbon compounds, except that now our root will be benzene. So as you saw earlier, bromobenzene, aminobenzene. Okay, so the name of the substituent group added as a prefix to the word root in case of monosubstitute benzene. Okay, this is what we mean, the bromobenzene, aminobenzene. Okay, but there are some cases like the benzene sulfonic acid. Now the group is written as a suffix, means it's written at the back part of after benzene. Okay, normally if it's a prefix, if it's a prefix, we're talking about it's in front of the word benzene. But now, because we are talking about this particular special case, okay, this is a special case. Alright, in special case, for benzene sulfonic acid, the sulfonic acid is written as a suffix, means it comes after the benzene word. Okay, these are special cases. So when 2 similar groups are attached to the benzene ring, the numerical prefix di is placed before the name of the group. Relative portion of the groups are indicated by suitable numbers or by the symbols O, M, or P. So O, M, or P means ortho, meta, or para. Okay, so as we mentioned in the previous slide, okay, if similar groups, like both of them are bromo, both of them are chloro, so you have to put the word di. This one must be there. Okay, if let's say there's 3 of the same groups, you use tri. But if it's tri, make sure you have to number them 1, 2, or 3, or 1, 2, 4, whatever lah. Alright, but okay, if it's just di, if it's just 2, then you have to put the dibromo. So if it's 2, you can see if the positioning is auto, meta, or para. Okay, you can use auto, meta, or para if you don't want to use the numbers. But if you want to use the numbers, also it is acceptable. Okay, so rule number 4 says when 2 different groups are attached, so now we have 2 different groups attached to the ring, names of both groups are added as prefix in alphabetical order. So if you have 2 different groups, right, you make sure you arrange them in alphabetical order. Okay, to the word root, so the word root is still benzene, and their relative positions are indicated. Okay, they are indicated. So like for this case, okay, 3-chlorotoluene. So toluene is methyl benzene, so automatically the carbon that holds the methyl will be carbon 1. Okay, so then you have to find the lowest number. Okay, the smallest value for chlorine, which will be 3. So nitrophenol will be 4. Okay, so here we have 2-bromo-iodobenzene. So 2-bromoiodobenzene. So in this one, you can, in this case, for the bromoiodobenzene, you can actually use auto bromoiodobenzene, or if you write, you can also write 1-bromo 2-iodobenzene. Okay, so the 2 here, I think there's something wrong. The 2 here actually is actually for, can't be bromo, because bromo has to be the first carbon because it is alphabetical order, right? So it should be 1-bromo 2-iodobenzene. Okay, so 1-bromo 2-iodobenzene. 1-bromo 2-iodobenzene. Okay, so this is following the alphabetical order. There are different groups. Or if you want to use auto, you can also use auto bromoiodobenzene. Is also an acceptable answer. So auto bromoiodobenzene is also an acceptable answer. So in the case of, okay, rule number 5 is talking about tri-substituted or higher derivatives. Position of group are indicated by numbers. So for more than 2, you must indicate them with numbers. Okay, you must indicate them with numbers. So this is a special structure, phenol. Okay, so if benzene ring attached directly to OH is called a phenol, not a hydroxybenzene, no such thing. Okay, so it's all called a phenol, as you can see here. Here we have very specifically. So even in IUPAC naming, we take phenol. Okay, we take phenol. This one also specific benzoic acid. This one also specific benzaldehyde. These are the ones that are special case. This is from chapter 4, whereby we have the aldehyde, the aldehyde group attached directly to benzene. We have the benzaldehyde. Okay, and then we have the benzoic acid as well, attached directly. So that is for naming. Okay, I hope you can cope with that, but no worries. We'll have some, I will give you some more questions for you to try, or some more examples for you to try your understanding, test your understanding. Okay, now we move on to stability and physical properties of benzene. So this part generally is a standalone. It is different. They will not ask you to compare the physical properties of benzene with the other groups. Okay, with the other groups. Benzene itself is unique because it is very stable. From here, they're showing you the difference between the cyclohexatriene and the benzene. So if we look at this, normally if you have a single double bond, this is what you call a cyclohexene. This is a cyclohexene. You will need this much of energy to break this bond, to break the double bond. Okay, so logically, if you have three double bonds, okay, by right the value should be multiplied by 3. You will get this amount to break all the 3 bonds. But in the case of benzene, the energy required is only lower. Okay, is lower. Right, is lower. Alright, so why does that happen? Okay, there's basically, it is due to the benzene's unique structure. So if, as you remember, okay, we have the benzene. Okay, we have the benzene, and then we have the delocalization of pi orbital. I hope you still remember this. It's from the first video. So because of this delocalization, stabilization energy or resonance energy, the low heat of anhydrogenation of benzene shows that benzene is a stable compound. So the stability in terms of benzene is a very stable compound. Okay, so in order to break all this bonding, it requires it requires lower energy, but in terms of stability, it is very stable. So it's not easy to break the bonds as well. Okay, it's very stable. Okay, you don't need to have based on the energy levels, okay, heat energy level diagram, okay. So the delocalization 150 kilojoules, okay. So the physical properties. So physical properties of aromatic compound like benzene, of course, the first one is aromaticity, aromatic. So the benzene have a characteristic smell. It is definitely a non-polar liquid. So non-polar liquid at room temperature. Instantaneous induced dipole dispersion forces, this is the intermolecular forces, and it should not be soluble in water because it cannot form hydrogen bonds with water, so hence it is immiscible with water. Now, this is the part that is very important for benzene's aromaticity. So aromatic character and Hakos rule, right? What determines the aromatic character? So not all how do you say, not all cyclic compounds are aromatic compounds. So in order to know whether a substance is an aromatic compound or not, it must fulfill the 4 structural criteria for a compound to be aromatic. So the first one is definitely cyclic, a cyclic molecule, a ring of atoms. 2, it must be planar, talking about the shape of it, okay, or in what plane it should be planar. And then 3, completely conjugated. Okay, completely conjugated, we mentioned about the conjugated system in the first video, okay. And 4, it will contain a particular number of pi electrons, okay, particular pi electron, okay. Now, cyclic molecules, so we have cyclic, to be aromatic, each p orbitals must overlap with p orbitals in adjacent atoms. On all 6 carbons of benzene continuously overlap, so benzene is aromatic. So this one we already stated quite clearly in the first subtopic where we talk about the structure. Next, a planar molecule. So all adjacent p orbitals must be aligned so that the pi electron density can be delocalized. So for example here, this is a cyclooctatriene, okay, octatetraene. Alright, although this is cyclic, but this is not a planar molecule. So this is the 3D drawing of the cyclooctatetraene. So because it is not in the planar, it's not in shape of planar, alright, so this is actually not an aromatic compound. Okay, so this is not an aromatic compound. Next, a molecule must be completely conjugated. So aromatic compounds must have a p orbitals on every atom. So both 1,3-cyclohexadiene and 1,3,5-cycloheptatriene contain at least one carbon that does not have a p orbital, so they are not completely conjugated, therefore not aromatic. Okay, so benzene, conjugated. So this one's not conjugated, this one not conjugated. So why is it not conjugated? So the explanation is here. Alright. Why does it need to be conjugated? Already we discussed it. Okay, we're talking about the delocalization of the p orbitals. And last but not least, Hakos rule. So Hakos rule is the one that it must have a specific number of pi electrons. Not the atoms, not number of atoms in particular, but the number of pi electrons. So Hakos rule, based on calculation, a planar cyclic molecule with alternating double and single bonds have aromatic stability of 4n plus 2n pi. So this is the formula. Okay, so n is 4n plus 2n electrons, right? So n is 0, 1, 2, 3, 4. So the number of pi electrons that satisfies Hakos rule. Okay, so if n is 0, 2, 1 is 6, 2 is 10, 3 is 14, 4 is 18. So in the case of benzene here, alright, it is 6. It has 6 pi electrons. So n is 1. For n is 1, for n plus 2, 4n plus 2 equals 6. Benzene is stable and the electrons are delocalized. There are 3 double bonds, 6 pi electrons. Okay. So components with 4n pi electrons are not aromatic, maybe anti-aromatic. diaromatic means they're not aromatic lah, basically. So for example, we have the planar cyclic molecule with 4n pi electrons are much less stable than expected. So these are anti-aromatic. Okay, they will distort our plane and behave like ordinary alkenes. Okay, so if you see a reaction later, if it's a cyclic, it does not necessarily behave like a benzene, although it is a cyclic alternating double bond. Okay, it looks like it has the conjugated, but because 4 and 8 electron compounds are not delocalized, they have the single double bonds, cyclobutadiene is so unstable that it diimerized by a self-Diels alter reaction at low temperature. Okay, so this is actually a very unstable substance, okay, unstable compound. So it can actually dimerize itself to form another compound. Okay, so cyclooctatetraene has 4 double bonds, reacting with bromine, K-manifold, and HCl as if it were 4 alkenes. So it is not an aromatic compound, so it does not behave, it will not undergo the reactions like the benzene. Okay, instead the kind of reaction that it will undergo will be similar like to the ordinary alkenes. So reaction of alkenes already you have covered in chapter 1. I hope you still remember. Alright, what other things to look at, how when the reactions occur, what are the bonds that are broken, and then what kind of product you will expect. So heterocyclic compounds contain elements other than carbon in a ring. So these are heterocyclic compounds. Heterocyclic compounds means they are cyclic compounds, but they're not only containing only carbon elements. Okay, they have another secondary element like nitrogen, sulfur, or oxygen or phosphate. So aromatic compounds can have elements other than carbon in the ring. There are many heterocyclic aromatic compounds, and many are very common. Cyclic compounds that contain only carbon are called carbocycles, not homocycles. Nomenclature is specialized. So this is a bit more advanced, but just a little bit introduction that some aromatic compounds not necessarily be just carbon, but also it can be a heterocyclic compound whereby there is other presence of other elements such as the nitrogen, sulfur, oxygen, or phosphate in their cyclic compound. Okay. So why for n plus 2? Where electrons fill the various molecular orbitals, it takes 2 electrons, 1 pair. I hope you remember. This is one of the rules, to fill the lowest laying, and then to fill the lowest laying orbital and 4 electrons to fill each of the n succeeding energy levels. Okay, so this is total of 4n plus 2. Okay, so this is a bit explaining to you why 4n plus 2. Okay, so this is just a little bit of extra information based on why the Hakos rule is 4n plus 2 and not what 6n plus 2. No, so we didn't actually just come up with it, as we like. So there is findings that I've already found, so it's definitely only 4n plus 2. Okay, so that is all for this video. We have already covered 2 subtopics, which is on the nomenclature, the naming of the compound, and also we discussed the aromatic character and Hakos rules. Okay, so we have covered the physical property part and the naming of benzene. After this, we'll go into the reactions. Okay, the reactions of benzene. So the reactions of benzene would be a bit slightly different from what you would see in alkene, and also probably carbonyl compounds. Okay, carbonyl compounds and alcohols. So for benzene is a little bit different. The reactions are a bit different. The conditions and the reagents used are also different. Okay, because benzene itself is a very stable compound. So when it's very stable, different kind of situation is required to introduce or substitute substituents onto the benzene ring. Alright, so that's all for this video. Continue. I see you in the next video.